People, in this video tutorial, I show you how you can model a plane strain or plane stress problem in a software such as 3D Experience, in this case release 2023X, which doesn't have a plane stress or plane strain element. Although I describe it for this platform, but it applies to any other package which this element is missing, but you still want to solve a plane stress or a plane strain problem. Just to remind people that the first exposure of undergraduates to uh, elasticity or finite elements is when they are dealing with the situation of plane stress or plane strain. And very often we want them to do certain problems, but the issue is that in certain software, such elements are not available, but the three-dimensional ones are available. Okay, let's move on for a second. Remember, this is not rocket science. It's just some tips that I'm going to give you on how to proceed. Let's recall what actually a plane stress problem is. Imagine that you have a sheet metal that is loaded in its own plane. Then there is very little stress through the thickness direction, and that's why we say the stresses are zero, and that's what the plane stress condition is. On the other hand, if you have a long structure, such as, for example, an earth dam, and there is maybe hydrostatic pressure behind it, then the strain in the axial direction, axial mean in this case, z direction is zero, but the stress is not. So that's the plane strain condition. What I just told you is essentially summarized in this table, but let's move on and see what happens, why this is, what was actually happening. So let's take the plane strain condition, okay? The relationship between stress and strain for a plane strain condition is given over here. Notice that there are no strains in the z direction. These are the strains in the z direction. This is the normal, these are the two shear ones. However, the stresses in the z direction, normal stress in the z direction is not zero. Well, these two are, but not this one. On the other hand, if you look at the plane stress condition, the stresses in the z direction, three of them, normal and two shears, are zero, but the strains, the normal strain is not zero in the z direction. Okay, that's why this thing actually contracts. Okay, Poisson ratio effect. All right, so how do I check this? Let me go ahead and take a plane. Uh, let's take a plane stress condition first. So we have a plate, think about it as a plate of thickness, of a given thickness here, okay? And dimensions are given there. Let's say that this is made of steel, and we apply a pressure at this end, which is 40,000 psi, okay? Tensile. Now, the stresses in this y direction are zero because there is no load applied there, and there's no shear strain in the xy plane either. Uh, the way I'm going to model this thing, I'm going to assume that this back face is on a roller, and I use, because I have three-dimensional elements, I use a three-dimensional element, one layer through that thickness direction, just one layer of through the thickness direction, and I'm going to use a very coarse mesh. So the size of the mesh is 0.5, which means basically we're going to end up with two elements here, but one layer through the thickness. Okay, and then what we're going to do is we find out how much this thing contracts. It better be this value. So this is how we're going to check. Now, in the case of the plane strain situation, I'm going to take a slice. Now, this is not the thickness, because remember, the thickness of this along the axial direction, z direction, along the z direction is essentially infinite, very long. So I'm going to choose the back face just like the previous case, put on a roller support, and the front face and the back face also on roller support. That will emulate or simulate the infinitely long, basically, object in the z direction. Okay, and the same pressure is applied. So we are going to find out what is the stress in the along the infinite direction, along this direction, and it better be this number. So I'm going to check this number. Again, a single layer through the thickness, a coarse mesh like that. All right, so let's go ahead and do that. The only thing that I have to watch out here for the illustration purposes, I am assuming that this plane, this object lies in the XY plane and Z is perpendicular to it. That's because I want to respect these uh, coordinate system. Okay, I want to make sure it looks like that. Okay, all right. So let's go ahead and do the which one first? We do the plane stress situation first. Let's go here. Okay, let me go ahead and make that block for you on the XY plane. I will sketch a, a, a rectangle of dimensions 0.5 by 1. So this is going to be 1 meter, 1 meter, and this is going to be 0.5, 0.5 meter. Exit. Let me fit this thing, and then we pad this thing. So we go pad it by 0.05. That's the size of the thickness of that slice or plate. I'm going to do plane stress first, by the way, although the geometry is going to be identical. Oops, a meter, 0.05, 0.05. Yeah, okay, good. Now, what do I make the material on it? Apply the material on it too. So I go to Tools, create a material. I'll call it steel plate, October 4, 2023. Okay, October 4, 2023. Say okay. It's going to create this here, right there. So let's apply, close this, apply to that. And now we're going to input the values, just the Young's modulus for steel. So under structures, general option, we don't need the density. Actually, we don't need the general option either. Abacus multiphysics, elasticity, and we put down 200 GPa, which is exactly the value that I want. 0.3, Poisson ratio 0.3. That takes care of this. I'm going to save this. All right, so now we're going to mesh it. So we go to 3D, structural model creation, empty FEM model. We're going to do the meshing ourselves. That's why I said empty FEM. I don't want it to go and automatically mesh things for me. So let's go to the mesh, and I'm going to do the sweep 3D mesh. So I click on that, I select that face, and in the description of the video, I said the size of this thing, I'm going to make 0.5 and one layer. 0.5, one layer. 0.5 meter, one layer. So you see that what's going to happen is it's going to create two elements for me. And these were, I'm sure these were linear. Let's make sure they are linear. Yes, right there. All right, good. So basically what I have is this model for you. You see that? So basically this is what I have. That is that guy. Okay. So we apply the properties. So properties, 3D solid section. You select this part, or you can select this. The whole thing is going to get selected. The proper material is going to be applied. You say okay. Good. So the property is created right there. All right. So now we're going to go to uh, you can either go to structural scenario creation or mechanical scenario creation. This is where you have some other licenses, such as for example, explicit dynamics, etc. But this is the straightforward one. You may not have the license to this, but in all likelihood, structural scenario creation, you have it. So you click on it. It's the structural problem that you're doing, and for the model, we use the one that we just created. Say fine. All right, let's go ahead and select our analysis. It's a static step. Okay, and I don't want to do any nonlinear or nonlinear iteration, so I'm going to uncheck this geometric nonlinearity because I wanted to do it in one shot, and this time, of course, is totally irrelevant. All right, so we created our step uh, or case, let's put it that way. Now we're going to apply boundary conditions. Let's put a roller on the back. We're doing a plane stress first, so there's only a roller on this back. So here is the slider. That's the same as a roller. You select that face, say OK. Now, and I'm going to apply, I have to apply two more conditions here, but I'll come to that in a minute. Let's apply the load here. I'll come back here in a minute. So load pressure on that face 40,000 psi minus 40,000 psi because I want to put it in the state of tension. There we are. The thing is that if I run this thing, it will bomb out because this can move, basically up and down and sideways under the roller. So what I need to do is to apply some other restraint here to basically uh, prevent the rigid body motion. And there are many different ways of doing it. What I'm going to do is the following. I will actually, uh, let me hide these because it's easier for me to pick my point when these are hidden. So I'm going to say, okay, where is that? I'll go to boundary conditions, fix displacement. So that corner point there. I'm going to fix it from going in, let's say, uh, uh, fix it going up and to the side. So that is up is Z. Let me see for a second. What I was hoping to do is to, yeah, that's good. This is in the XY plane. Very good. So I'm going to fix it in the direction uh, Z and up is X. Up is X. Okay, that's good. And this other corner point, right now I can hinge about that, but this other corner point, I'm going to fix it in going from in the direction X. That'll prevent the rigid body motion. Now, if I run this thing, you'll see that it'll work. So let's see now, go to simulation. Let's do a quick model check in case there's any obvious thing that we missed. That's fine. Let's do a quick simulation check. I don't anticipate any problems here either. Remember, this is the plane stress condition, and there we're going to look at the contraction in the thickness direction. It should come out to be plane stress. It should come out to be this number. Displacement should be minus 3, 10 to the minus 9. Okay? We wait for this thing to finish. It's done. And now we're going to run it. That's going to be in only 2 increments because I unchecked that nonlinearity thingy, and it's going to do the initial step and the final result. All right. If you look at the iteration, rows, it says just 0 and then 1 probably. Yeah, there, 1 or 2, 1 and 2. Okay, this is the final one. It's going to be extracting result there. Okay, 2 steps right now, 2 increments. Very good, 2 increments. All right, so let me close this. So how do we check our stuff? Well, this is the first, this is before we apply any load, and there is applied load. That does not surprise you. All the same color, all 40,000 psi. That is not a something complicated. You apply a uniaxial load here, 40,000 psi. Everything is going to go to 4,000 1000 psi. Now the question, how do we check this number, the displacement? So we go here, where is that? We go there and ask for displacement. Well, first of all, if you don't like the smooth coloring, so double click on this legend and say, don't show it to me using smooth colors. Okay, good. Now, I want to see the displacement, but this is the magnitude of the displacement. I don't want the magnitude of the displacement. So I double click on this and select this edit, right? No, that's okay. I double clicked on that and there's a definition box here. See that? You expand the definition box, you want the translation, but you don't want the magnitude. You want the direction 3, component 3, because remember the way I made it, this is made in the XY plane, and in the thickness direction, that's direction 3. So if I say okay, there we are. Notice what happened right here. On this side, this thing contracts, displaces, moves by the amount -3 e to the -9, which is this number. Okay, so we have solved a plane stress problem with a 3D element. Okay, the trick was to put one layer through the thickness, and that's pretty much it. Okay, now let me go ahead and, incidentally, if you look at here, if you look at this, the stress through the thickness is 0, and if you don't believe it, let's go ahead and do that. So let's plot the von Mises stress. There's the von Mises stress. Double click on it, and once again make sure the definition checkbox is expanded like that. You want the stress, but which component? Direction 3. So where's direction 3? Not Mises equivalent. We want direction 3. So scroll down here. Okay, I have to move this thing so that I can see the rest of the stuff. Where is this? Component 3. Oh, here's component 3. And when I say apply, I better get 0. And I do get 0. Don't let these colors fool you. Look at the powers. It's the von Mises stress in Pascal, 10 to the minus 10. It's all 0. This is all numerical junk there. All right, so let's go ahead and do the problem with the plane strain now. For the plane strain condition, we have to put a surface slider on this side and surface slider on the other side. Incidentally, when I do that, some of the stuff that I put up here is unnecessary. In fact, I'm gonna fix that to convince you that I don't have to actually do all those two restraints. But it doesn't matter. You can leave it the way it is, but I'll change it. Okay, so let's go ahead back to the scenario. There we are. And I put a surface slider once again, boundary condition, surface slider or slider on that face. If you're having a problem, that's because the mesh is in front of you. Cancel that. Right click visibility manager. Don't show me the mesh. Good. And close that. So let's go ahead and get a surface slider there. Okay. And there. Now, because these are on surface sliders, this thing cannot go sideways anyway. The only thing that I have to do is 1 point, not going up and down. I can leave it the way it is, but it's unnecessary. So let me go ahead to that structural under boundary conditions. This one I'm going to delete, completely delete. That first one I'm going to delete. Good. If I run it, this should give me the results for plane strain. So let's go ahead and simulate. I'm going to run this thing because I know that nothing is going to happen here. It's a good idea to do the model check and scenario check, but I'm eating my own words, not doing it. Let's see now, under iteration, there's going to be two increments, basically, the initial and the first one is going to be done. And then the thing that we have to check is stress in the direction 3 must be 1.2 10 to the 4 Pascal. So let's wait. It's all done. Yeah, it's not done yet. Now it's done. So close that. So if you look at the von Mises, this is, let's look at the von Mises stress, or it is von Mises stress. Double click on that, but I want the stress in the, this is stress component in the direction 3. So direction 3, which is exactly what we have. This better be 1.2 10 to the 4. 1.2 10 to the 4. Okay? And this is the stress. Obviously, if you check the strain, if you plot the strain, you're going to get 0. Okay? So I showed you, if you have a software such as 3D Experience, which buried in it, of course, is the Abacus program. However, they don't have the plane stress and plane strain implemented in 3D Experience. Okay? So if you want to fool it to do a plane stress or plane strain problem, I showed you what to do. Namely, you make 3D, one layer through the thickness, is plane stress. Don't worry about the faces, but if it's plane strain, then you have to put the restraint appropriately to mimic the fact that this is infinitely long and it doesn't have any strain in that direction. A good example, another example is the CATIA program, which has buried in it an FEA solver, which is called Elfini. There also, all the elements are three-dimensional. Now, one other thing, the plane stress problem that I did for you can also be done with shell elements. In other words, you model it with shell elements. It's just that because everything is in the plane stress, all the deformation happens in the plane of the that shell, and therefore rotations are not important. But I'm not going that route. It is possible to replicate a plane stress problem with shell elements. That's not what I did though. All right, good luck.